Okay, so we're going to go through and find the first derivative. We're going to do that with respect to x for each one of these pieces. The derivative of x squared with respect to x is just the power rule, and that would be 2x. The next portion, the derivative with respect to x of y squared, the first thing I need to know is understand that that implies that I need to write down that this is the derivative of my variable y with respect to x. Then I can use the power rule on write that as 2y, and all of this is equal to 0. Now the first thing I want to go ahead and do is solve for dy dx. So solving for dy dx, I get that by moving the 2x over, which would give me a negative 2x. Then I would divide by 2y, or dy dx is just equal to negative x over y. All right, we're going to use this in a second. But what I want to find for this question is a second derivative. I want to find d squared of y, the second derivative of y, with respect to x. Now, in order for me to do that, I need this idea of dy dx is equal to negative x over y. So I'm going to go through and plug that in. So right now I have 2x plus, I substitute back in that I have negative x over y. I multiply that times 2y is equal to 0, or I get 2x minus 2x, and I get 0 is equal to 0. So I can't use simple substitution with this. I actually have to go all the way back, and we're going to go all the way back up to here and start with the fact that I know this up here is true. I know that dy dx is equal to negative x over y. And what I have to use now is the quotient rule. I'm going to go ahead and take dx of both sides. When I do that, I am now left with the second derivative of y with the derivative of x squared is equal to, now I need the quotient rule, my numerator is negative x, the derivative of my numerator is just negative 1. Now, where this gets a little tricky is the fact that v is equal to y. So when I go through and find dx of y, I still need to use implicit differentiation. So v prime is going to give me dy over dx times 1. Now, to go ahead and put that in there, it's the derivative of the numerator times the denominator, which is just negative y. Then I subtract out negative x times dy dx, and that's all over my denominator squared, which is over y squared. Now we're going to go back and try that substitution trick again. We said before that dy dx, I can substitute all of that out and replace it with negative x over y. So let's go ahead and try that and make that equal to negative x over y. Now my second derivative is equal to negative y minus x squared over y all over y squared. In order to simplify this is a complex fraction, so I'm going to multiply both the numerator and denominator by y. leaving me with negative y squared minus x squared over y to the third. And we can even simplify this more. Let's take a look back up in the beginning. If we are looking at this, I can take out a negative, and then I'm left with x squared plus y squared all over y to the third. But remember what our original equation was? Our original equation was x squared plus y squared is equal to 1. So all of this, the second derivative, is equal to negative 1 over y to the third. And that's again because in my original equation, what did I say? I said that x squared plus y squared was equal to 1. So I just made that substitution. Okay, so again, we want to do implicit differentiation on this. So we're going to take dx on both sides, and that's because I want to find, the question for this would be to find the second derivative with respect to x. So I find the first derivative, and I am left with 1 is equal to dy dx is equal to, now I'm using the chain rule here, and I needed to write down dy dx because this is asking me for the derivative with respect to x. My variable is y. That's why you need this implicit differentiation portion, and this allows us to write a single unified derivative of dy dx. I use the power rule on y to the third and get this is multiplied times 3y squared. I want to solve now for dy dx. Divide 3y squared on both sides. And you are left with dy dx, my first derivative, is equal to 1 over 3y squared. I want to go ahead and rewrite that as dy dx, my first derivative, is equal to 1/3 y to the negative 2. To find the second derivative, take dx of both sides again. Thus, over here on this side, d dx of dy dx, that gives you the second derivative of y with respect to x. Now we're going to find the derivative with respect to x again, but again, because it's with respect to x and this is a y here, I need to have the fact that this is equal to dy dx. Then I can use the power rule. That's 1/3 times negative 2 y to the negative 3. And here what I want to go back and use is the substitution that dy dx is all equal to 1 over 3y squared. So I replace all of that with 1 over 3y squared, leaving me with the second derivative of y with respect to x is equal to 1 over 3y squared times 1/3 times negative 2. I'm going to bring that y to the negative 3. I'm going to move that back to the denominator so it's positive. And I am now left with negative 2 over 9y to the 5th power. So we're going to go through and find the second derivative. Hopefully by now this notation is getting more familiar. I take d dx of both sides. The derivative of x is just 1. The derivative of y is what we're taking with respect to x, so I must write that down. And now I use the power rule of y to the 10th, and I'm left with this is times 10 y to the 9th. I go through and I solve for dy dx by dividing both sides by 10y to the 9th. And I'm left with dy dx is equal to 1 over 10 y to the 9th. And I'm going to need to use that in a little bit. Going back to what I just had, I now dy dx is equal to 1 over 10. I'm going to write this as y to the negative 9th and take the derivative with respect to x of both sides again, leaving me with the second derivative of y with respect to x squared. And again, because I am taking the derivative of y with respect to x, I need to write that down. The 1/10 comes along. I use the power rule on y to the negative 9th. So that becomes negative 9 times y to the negative 10. And I want to use this substitution again. I said before that dy over dx was equal to 1 over 9. 1/10. So I'm going to replace that, and now I'm left with 1 over 10 y to the 9th times 1 over 10. Let's just put that negative 9 up there and bring that y to the 10th down. So now when I multiply across, I'm left with negative 9 over 100 y to the 19th power. And we have to not ignore the trig functions when finding the second derivative. So we're going to go through again this first time, first taking the derivative with respect to x for both sides. When you do that, the derivative with respect of x, that gives me 1. Now, this is asking me to find the derivative with respect to x, but my variable is y. I need to write down that this is the derivative of y with respect to x. Then the derivative of the sine of y comes down and is just the cosine of y. Solving for dy dx, I get that dy dx. And again, what I'm doing here is I'm dividing both sides by the cosine of y. And I get that dy dx is equal to 1 over the cosine of y, which is also the secant of y. So that's just the first derivative. Now I need to take the derivative a second time. Again, it's d dx of both sides. So that leaves me with the second derivative of y with dx squared is equal to, again, I need another dy dx because I am taking the derivative with respect to x, but my variable is y, so I need to include that is what I'm saying. The derivative of the secant of y is the secant y tangent of y. Then I go back up to what I know. I know from the beginning that I said that dy over dx was equal to the secant of y. So I go ahead and replace this with the secant of y. So now I have the second derivative of y with respect to dx squared is equal to the secant of y times the secant of y times the tangent of y, or all of that is just equal to the secant squared of y tangent of y.